You should never get an azimuth problem on a Coast Guard exam wrong ever again, and here's why. There's a bulletproof solution if you follow the steps that will result in the correct answer every time. This is the formula that you need to know, but you don't need to memorize it. There's also a series of rules that you need to apply in order to make sure that the formula works for you every time, but you don't need to memorize those either. They're located in Bowditch. Let me show you where. So if you're using the 1981 edition of Bowditch, it's on page 505, and here's a discussion all about solving for azimuths. And this formula 4a is the one that you're going to want to use. And then there's discussion about the sign convention. So if you get into the exam room, you're a little flustered, you can just kind of review this stuff and make sure that you hit all those sign issues, and this formula should be bulletproof. You might use this one instead. It's just the same thing, just rearranged, but this is kind of the quickest and easiest one. If you're using the 2019 edition of Bowditch, which is the current one in the Coast Guard test rooms as of this filming of this video, it's on page 235, and then there's a shorter discussion about azimuth angle, but it does talk about the formula. You'll notice it's a little bit different. It puts the tangent inverse on this side, but it's the same kind of thing. And then it talks about the sign convention there as well. So don't memorize this stuff per se. Just be sure to find where you can look it up and you'll be good to go. So in order to use this formula, we need to pull 3 values from the stuff that the Coast Guard gives us. The first is LHA. That is the local hour angle. If you've been studying celestial navigation or navigation problems, you're familiar with what that is. L is the latitude. That's going to be the latitude of the vessel, your latitude to the nearest possible number that you've got. And then finally, there's D for declination. That's going to be the latitude of the geographic position of the sun, which we look up in the Nautical Almanac to get that information. All right, these 3 values are going to be calculated in decimal notation. So for example, if you had 25 degrees and 30 minutes north for your latitude, you need to turn that into decimal degrees. So you may be able to do this one in your head, but if you take the minutes that's in a degree and minute presentation, if you take the minutes and divide it by 60, that will turn things into decimal notation. So 25 and then 30 divided by 60 is 0.5. So that would be the way to get the numbers into decimal notation. If you struggle with this, practice that until you're comfortable with that skill and then move on to the rest of the problem. The other part that we really need to talk about is kind of this thing called course angle notation. Now, if we're out there on our ship, we use a 360-degree compass to give bearings to things. So directly north would be 0, 0, 0. Directly east would be 0, 9, 0, for example. However, when we're doing trigonometry, which is the mathematics of angles and triangles specifically, usually we're doing the math on what's known as an included angle, the angle on the inside of a triangle. So with a celestial navigation problem like an azimuth, you're creating a triangle between your position, the geographic position of the sun, which is the spot like directly beneath it at any time, and the north or the south pole. Once you do that triangle, this included angle is the number that we punch into the calculator or the number that the calculator punches out at us. If we want to convert this into a true compass direction for our ship that we can actually point at, we need to apply some azimuth rules. Those rules are going to be here and they're located in Bowditch. So when the outcome of the problem is spit out of the calculator, you do need to also be sure to apply these azimuth rules. As an aside, if you're doing really any celestial navigation or even sailings problems like Great Circle or Mercator sailings, this course angle notation thing is really important. So there are ways that you can memorize rules for like the sailings, how to change things over, but I really just recommend remembering that when you're doing this stuff, you're doing triangles and you're solving for the interior angle of a triangle, whereas our maritime world is sometimes that and then sometimes it's different. Generally speaking, if you're heading northeast, it's going to be the same, but otherwise you're going to need to do like 360 or 180 from it in order to get a true compass direction that you can use. All right, so with that said, let's take a quick look at Mathematics 101 and then we'll dive into our problem. The first quick thing I want to review is the general rules of algebra. So if you're ever using an equation, which is a thing with an equal sign in it, you can do things to both sides of the equation as long as you balance them out and do them the same. So for example, if you had 10x equals 20, you probably know the answer if you're studying for your exam, but just to reiterate what you can do, you can divide both sides by 10 because you're doing it to both sides. And then in this case, the 10 over 10 cancels out, and you're left with x equals 20 over 10, which you can type into a calculator such that x equals 2. The same thing is going to apply when we do this big trigonometry formula. It's really just algebra with large numbers in there. So when you have tangent of z on one side, if you end up with some number on this side, you can do what's known as take the inverse tangent of both sides of the equation. So eventually you're going to work your way down through this and you're going to have tangent z equals some number. If you just do inverse tangent to both sides, that's going to spit out a correct value. That value is going to be z. Z equals, some number. Remember though, that is the interior angle of a triangle. Sometimes it matches your course, but most times it doesn't. So you need to take this z value and apply these rules to get what's known as Zn, or your true azimuth. The last thing to mention before we get started is going to be the calculator functions. Every calculator is different, but generally speaking, these are the things you want to watch out for and be familiar with. Number one is the numbers that are down here, and then the functions that you can use. But for our purposes, the sine, the cosine, and the tangent functions are right there. So let's just say you had 45 degrees and you took the sine of it. It's going to output something 0.7071 there. And I would say that if you're very comfortable with the calculator, you can program the memory of these and solve this equation very quickly. However, it's often just easiest to write down 0.7071 and then get back to it pencil and paper kind of thing. I would recommend 4 decimal places for these type of celestial navigation calculations. Note that value though, 0.707, we took the sine of 45. Let's just take 135 degrees and take the sine of that as well. It's the same darn thing. Why is that the case? Well, again, this refers to that coarse angle notation. A triangle is a triangle, whether it's upside down, inside out, or rotated. And so sometimes these values are going to spit out the same thing, and that's why we have these azimuth rules to get the correct true bearing to something. The other thing that I want to mention is, let's say you had some value and you wanted to then take the inverse tangent of it. An example on this calculator, you would press the shift button and then tangent to get the tan -1. And that's going to output 35 degrees. So the inverse tangent of 0.707 is 35 degrees, which you could then apply azimuth rules to figure out your true bearing. All right, so get familiar with your calculator. If you are very comfortable with it, you can definitely program things in and do this all in one step. And if not, do it like we do on the whiteboard, where we kind of keep track to 4 decimal places of each thing. All right, now it's time to tackle the Coast Guard problem, which I'm showing you up on the screen now. So the first thing to know about this problem is that there are going to be 3 phases to it. The first is going to be a chronometer problem, which hopefully you've been studying elsewhere. The second step is going to be this azimuth stuff, which we've been talking about. And then the third step is going to be a compass problem, specifically a gyro compass problem in this case. The Coast Guard loves to combine skills to really test you, so that's what you can expect on your exam. The first part then is going to be to tackle the chronometer and find out when this all actually occurred. All right, so the first thing to know is that we took our site at 0706 zone time, and our DR longitude was 85 degrees 35 west. All right, so if you take that 8530, divide it by 15, it'll tell you that your zone descriptor is +6. You're 6 hours to the west of Greenwich, okay? So that means the Greenwich time was approximately 1306 GMT, but that's not good enough for our purposes here. It also says that the chronometer was 01:03:30 when we took the site. Chronometers are set to 12-hour time, so you never know if this is 01 or if it's 13 hours. Always be aware of that. chronometers are also set to GMT. So hopefully you can see like, all right, it's going to be 1300, but you do need to reason through those steps just to make sure. It also says that the chronometer was 2 minutes and 30 seconds slow. All right, so if the chronometer is slow, that means Greenwich time happens first, and then 2 minutes and 30 seconds later, my watch says Greenwich time. So we need to add this 2:30 to get them in sync together. Very good band. So 01:06:00 GMT is the correct chronometer time. And we previously said this is not actually 01, it's 1300. All right, so a few steps to that chronometer. Number one, take your zone time, figure out your zone descriptor, then figure out your GMT approximately, and then do your chronometer correction. It might be slow, might be fast, there might be some rate that they give you, but either way, you need to get a GMT solution. Moving on, our second step is to solve the azimuth. And in order to do that, we really need three pieces of information. We need latitude, we need declination, and we need LHA to use this formula. All right, so I'll just erase this stuff that we've already done. And now we're going to go on a quest for those three pieces of information. For latitude, we've really got it already. The problem gives us our DR latitude, 25 degrees, 30 minutes. We need to convert that to decimal notation, but I think you can do that in your head, and it's 25.5 degrees north. All right. Can we do anything with declination or LHA yet? No, we can't. So in order to do that, we need to take 1306 GMT on the 6th of November and go find the answers in the Nautical Almanac. Let's take a look at that in the daily pages. And we'll pull out the GHA and the declination for 13 whole hours. So for 13 whole hours, the declination is on this side and the GHA is on this side. It's 19 degrees 05 for GHA. All right, and then for declination, it's south 1603. You also want to note the trend in the direction of declination, so it's getting bigger, so we'll make a little plus sign for that. And then lastly, we want to look at the little D number here. D is 0.7. That just represents the difference from hour to hour, basically, but we need that for the next part here. All right, so our GHA right out of the book was 1905, and we need to account for those 6 minutes, so we'll do that in just a second. And then our declination was 1603 south right out of the book. We need to account for some stuff, but first we need to note the D number, which was 0.7, and we also note the fact that the declination is increasing from hour to hour. Not the D number increasing, but the declination itself. So then we can go into the increments and corrections pages. So that's the daily pages. We'll take that information and then we'll go back to the increments and corrections for 06 minutes. That's the amount of time we have not yet accounted for. So 6 minutes and 0 seconds. The sun is going to move 1 degree and 30 minutes. So we need to add that to the GHA to get the total GHA for 1306. And the D number that we said was 0.7. That just is a correction factor. So that means we need to take the value next to the correction factor, which is 0.1. Earlier we said it was increasing in the daily pages, so we're going to add 0.1 to it. So we can correct our GHA to make that 20 degrees and 35 minutes. And then for our declination, we can correct that with the 0.1 to make it 16 degrees 03.1 south. All right, so declination is good. Why don't we first convert this into decimal notation and get that up into our solution board here. So 03.1 divided by 60 and then add the 16 degrees will give us the 16.05 degrees, and it is south, okay? South. For GHA, first thing let's add 360 degrees. You can always do that to make your numbers a little bit better. So it's 380 degrees and 35 minutes. And then in order to get LHA, the rules are if you take the GHA and then in the Western Hemisphere you subtract your longitude, you'll get LHA. If you're in the Eastern Hemisphere, you add your DR longitude to get LHA. You've probably worked on this on other stuff, but just to say those rules. So in this case, we need to subtract our DR longitude, which was 8 8535. Coast Guard did us a solid by making the numbers a little bit easy to do, and so our LHA is 295 degrees. So we can put the LHA up here, and now we've got our three numbers. But before we hand jam those into the formula, we need to make sure that our sign rules are correct. So if declination and latitude are contrary or opposite, that means declination is negative. So let's make this a negative number. And then if LHA is greater than 180, LHA is negative as well. So let's make that a negative number as well. So latitude is going to be positive, the others are negative. So now we can enter that information into our calculator and see what comes out. Join me on that expedition. Okay, so we'll take this formula and we'll just work one at a time. We'll put things in. So LHA, negative 295, sine. So I get plus 0.9063. And I'll just ignore this tan Z so we can keep the board clean here. The next one, cosine L. Latitude is positive, 25.5 cosine. What do you get? 9026, 0.9026. I use parentheses to keep myself organized there. The next one, tangent of D. D is negative, so 16.05 negative tangent. And that will give you your result, and it should be negative 0.2877. Then the formula says to subtract, and we got two more values here. Sine of L, so 25.5 sine, and we get 0.4305. And then the last one, cosine of LHA. LHA is negative 295, negative cosine. That should give you your result for 0.4226. So now we got our numbers, no more sines and cosines for a while. We can kind of work algebraically through this. So we'll leave the numerator alone. 063. And then we'll work on this. So 0.9026 times 0.2877 negative should give you negative 0.2597. So that's 1. Subtract 0.4305 times 0.4226 should give you 0.1819. Make sure you're getting the same stuff as me as we work through this. So now we subtract in the calculator. We'll do 0.2597 negative minus 0.1819 to get negative 0.4416. We'll bring the numerator down, positive 0.9063. And now we can really put this into the calculator. Just don't forget that negative sign, and you'll end up with tangent Z equals negative 2.0523. All right, so that's just calculator work. If you got the same results, we're on the same page. That's not the answer though. We need to take the inverse tangent of both sides. So negative 2.0523 shift tangent should give you Z equals negative, basically 64. You don't need to go too much crazier than that. All right, 64 degrees. Is that the answer? Sometimes, not always, not usually, in fact. Next thing we need to do is apply our rules here. So are we in the northern latitude or the southern latitude? All right, we're in the northern latitude. LHA is greater than 180. You can ignore the negative sign for this part. So Zn equals Z. All right, so we're good to go there. Those rules are good. If Z is negative, which it is, right there, add 180 degrees. So negative 64 plus 180 equals the true value of 116 degrees. All right, so that's an example of this coarse notation stuff where the included angle for math was 64 degrees or negative 64 degrees in this case, but the true value, our compass value, is going to be 116 degrees. All right, so that's the azimuth portion. Now we can work on the compass portion. If you remember the acronym GET for get, gyro plus easterly error is true. So 116 degrees true. The problem stated it was 114 degrees per gyro compass, so the difference is 2 degrees. Then you need to figure, is it east or is it west? Gyro plus easterly error is true, so it's going to be east. Gyro best, error west. Gyro least, error east is another way to remember that. All right, so this process was long, but that's how it works for Coast Guard exams. We solved a chronometer issue. We solved an azimuth issue by using this formula, which again you can look up in Bowditch, and applying these rules to it. And then we solved a compass problem to get the Coast Guard answer. All right, good luck on your exams.